In this lecture, we explore logarithms. Here's an analogy of how to think of logarithms. What does a square root mean? What do we mean by the square root of 3? We mean to find a number so that when it is squared, the result is 3. The number 1 is too small, since 1 squared is 1, while the number 2 is too big, since 2 squared is 4. Let's try 1.5. Since 1.5 squared is 2.25, the square root of 3 needs to be higher than 1.5. Let's try 1.7. As 1.7 squared is 2.89, it seems that the decimal for the square root of 3 starts out as 1.7, and we explore further decimals after 7 if we want to be even more accurate. That's the meaning of square root. In the same manner, we can think of cube roots or third roots. When we write the cube root or the third root of 2, we mean to find a number that when cubed, or when raised to the third power, will result in 2. Since 1 to the third power is 1 and 2 to the third power is 8, the number needs to be somewhere between 1 and 2. Let's try 1.5. As 1.5 to the third power is 3.375, it's too big. Let's try 1.2. As 1.2 to the third power is 1.728, that's too small. Let's try 1.3 to the third power, that's 2.197, and this is also too big. So the third root of 2 needs to be between 1.2 and 1.3. We can next try 1.25 to become more accurate, and continue this procedure until we found a few decimal points. Of course, this is all done immediately on a calculator to avoid this time-consuming work. And there's nothing special about square or cube roots. We can have fourth roots or fifth roots and so forth, in which we write x to the nth root, which is the nth root of the number x. So what exactly are nth roots? They are the backwards or inverse operations of finding exponents. The meaning of x to the n power is to multiply x by itself n times, where n is the number of the exponent. The meaning of x to the nth root is to find a number that when it is raised to the power of n will result in x. Thus, we see that the nth roots are in a way the backwards or inverse operation of finding exponents. Rather than finding what some number is raised to a power, we find a number that when raised to the given power will result in the number that we want. The idea of logarithms is similar to this. Let b be a positive number, as it will be the base of our exponent. The meaning of b to the x is to raise b to the power of x. As we discussed previously, we can allow x to be negative or even a fraction. And we can determine b to the x so that we know how to raise a number to an exponent. The logarithm is the backwards operation of raising exponents of b. The notation we use is log b to x. And we read this as the logarithm of x with the base b. The meaning of log b to x is that the number which b has to be raised to in order to get x. Instead of finding b to the x, we need to find what b needs to be raised to produce x. If you find it helpful, you can think of log of x with a base b as the solution to the following problem. B to the question mark equals x. Let's look at some examples. Let's find logarithm of 4 with a base of 2, logarithm of 3 with a base of 3, logarithm of 1 with a base of 5, or logarithm of 0.5 with a base of 2. Let's start with the first one, logarithm of 4 with a base of 2. If question mark equals logarithm of 4 with a base of 2, that means 2 to the question mark equals 4. Clearly, 2 to the second equals 4. So therefore, log of 4 to the base 2 is 2. With log of 3 with a base 3, we need to solve 3 to the question mark equals 3. Since 3 to the first equals 3, it follows that a log of 3 with a base of 3 equals 1. Now with a log of 1 with a base of 5, we need to solve 5 to the question mark equals 1. Remember that the 0 power is always 1, so 5 to the 0 power equals 1, meaning that a log of 1 with a base 5 is 0. Finally, log of 0.5 with a base 2, we need to solve 2 to the question mark equals 0.5. If the exponent is negative 1, then by the rules of negative exponents, we see that 2 to the negative 1 equals 1 over 2 to the first, which is the same as 1 over 2, which is 0.5. So a log of 0.5 with a base 2 equals negative 1. Here's a useful reminder. It's a common mistake for students when asked to find log of 4 with a base 2, for example, to think of the question as asking 4 to the question mark equals 2. How do we remember that when the logarithm is asking, the problem in this case is 2 to the question mark equals 4 instead? Well, the number at the bottom of the logarithm is the base of the logarithm. Therefore, it's also the base of the exponent. When we see log of 4 with a base 2, we interpret this as asking the problem 2 to the question mark equals 4 because 2 is the base of the exponent 2 to the question mark. Just like we have x to the nth root for different numbers n, so do we have different kinds of logarithms of log of x with a base b, depending on what base we choose. We're accustomed to the fact that roots, or cube roots, or square roots, or any kind of roots don't have to produce integers. For example, the square root of 2 is no longer an integer like the square root of 4 is. Unlike the square root of 4, which is simply 2, which is a whole number, the square root of 2 can only be approximated by a decimal of 1.414, etc. It's an irrational number, so the decimal points never actually end. When dealing with logarithms, similarly, we need to also get accustomed to the fact that logarithms very often do not produce nice whole numbers. They can also be decimals, which can be never-ending, like with radicals. For example, let's determine log of 3 with a base of 2. Here we need to solve the problem 2 to the question mark equals 3. We note that 2 to the first equals 2, and 2 to the second equals 4. So 1 is too small, and 2 is too big. Therefore, a log of 3 with a base of 2 must be some number between 1 and 2. Let's try 1.5. On a calculator, we can compute 2 to the 1.5 power equals 2.828, which is still too small. Let's try 1.6. 2 to the 1.6 power, we can calculate to 3.031, which means that 1.6 is a bit over log of 3 with a base of 2. So log of 3 with a base of 2 is some number between 1.5 and 1.6. If your calculator can compute logarithms, you will get that log of 3 with a base of 2 is 1.584, etc. This, as we can see, is close to our guessing approach that we discussed. Of course, there's no need to find logarithms by guessing, as calculators have a built-in command that does such computations. We did this small computation just to explore the concept of what a logarithm is. Before we move on, a couple of caveats. First of all, the base of a logarithm is not going to be 1. So in our example, where b is the base, b is not equal to 1. We're never going to come across a problem such as the logarithm of 5 with a base of 1. The reason for this is that the logarithm just won't exist. Logarithm of 5 with a base of 1 is the solution to the problem 1 to the question mark equals 5. Since 1 to the anything is 1, there's no way to get 5. Logarithms also don't exist if the base is a positive and the number is a negative. For example, logarithm of negative 1 with a base of 2 is impossible. There's no way to raise an even number to a power and get a negative number in response. If they're both negative, it can exist. For example, logarithm of negative 27 with a base of negative 3 is fine, since negative 3 to the third power is negative 27. But you cannot have, for example, logarithm of negative 27 with a base of positive 3, or any other positive number for that matter. Since b to the first equals b, it means that a log of b with a base of b equals 1. And since b to the 0 equals 1, it means that the log of 1 with a base of b equals 0. In other words, the logarithm of the base is 1, and the logarithm of 1 is 0. The next rule of logarithms is that a log of x times y with a base of b is the same as a log of x with a base b plus a log of y with a base b. In other words, the logarithm of a product is the sum of the two logarithms. For illustration, consider a log of 25 with a base of 5, and log of 125, also with a base of 5. We know that a log of 25 with a base of 5 is 2, since 5 to the second power is 25. And we know that a log of 125 with a base of 5 is 3, since 5 to the third power is 125. Now, by the exponent rules, 5 to the 2 plus 3 power is the same as 5 to the second power times 5 to the third power, which is also the same as 25 times 125. And so the logarithm of 25 times 125 to the base of 5 is the same as the logarithm of 25 with a base of 5 plus a logarithm of 125 with a base of 5. Why is this true? Well, let x equal log of x with a base of b, and let y equal log of y with a base of b. And so b to the x equals x, and b to the y equals y. When you multiply them together, or b times x, or b to the x exponent times b to the y exponent, that's the same thing as x times y in the exponents. So that means that b to the x plus y is our answer. Put back into logarithm terms, that's the same as log of x with a b base plus log of y to the b base. Another important rule with logarithms is that the log of x to the p power with an overall base of b is the same thing as p times the log of x with a base of b. In other words, the logarithm of some power is the same thing as the product of the logarithm with the power. Basically, you can just take the power of whatever the logarithm is and multiply it by the entire expression. For illustration, let's take log of 25 with a base of 5, which of course is 2, since 5 to the second power is 25. So therefore, log of 25 to the second power with the base of 5 is the same thing as 2 times log of 25 with a base 5. If we change it for numbers, we see that it works, as 25 to the second power is 625, and log of 625 with a base of 5 would be 4, and if we did it the other way, or 2 times the log of 25 with a base of 5, we would also get 2 times 2, which is also 4. The second expression, log of 25 with a base of 5, would also be 2, since 5 to the second power is 25. Of course, don't worry if you have trouble understanding the justification for these rules. Just make sure you know the rules and how to use them.